So thanks again for the opportunity of being here. I will talk about MetroHaul. I would thank Victor because he introduced some of the concepts that I would like to talk about today. But maybe we should see this from a research perspective. It's a research project. Also from a perspective of a transport network is some aspect that is not usually considered when talking about NFV orchestration. And without many details, I would like to go into the outline of the talk. Very briefly, MetroHaul deals with designing the next generation of metropolitan networks. It means that we will have new metropolitan nodes with low-cost optical switching and transmission and computing and storage. You will be hearing the term optical cloud and photonic cloud quite often. And the ultimate goal also in this 5G PPP platform is to be able to offer 5G services and network services. Today I will address a couple of challenges. One of them is going to be what we call disaggregated transport networks. And how do we address SDN control of these transport networks? It includes betting on a huge model-driven development. And I will also address the second challenge, which in common with Tango, which how do we do NFV orchestration in these networks? And how do we address 5G network slicing? And one of the main challenges is how do we map this idea of 5G network slicing to the idea of optical network virtualization, which has been running around for a few years. So the goal of the project, what do we set as the main goal of the project, was to design cost-effective, energy-efficient metropolitan networks. The goal was we need to be scalable for heterogeneous 5G access. We need to address the anticipated capacity, huge bandwidth requirements, latency requirements, and coming from an optical world, I do defend and state that the optical technology is the one that has to be there to ensure these KPIs. But of course, we need to support a wide range of services, use cases. Victor talked about the verticals. This is also in the scope of this 5GPP program. And at the core of this project is the design of new optical metro nodes. These optical metro nodes have something in common with core initiatives that you heard of. These optical cloud, in short, they are big nodes that encompass many types of resources, packet switching, circuit switching, optical, storage, computing, and so on, and that have to interface between 5G access and core. So at the core of this is also the design of a console orchestration and management system. We are reusing existing SDN and FB frameworks, and we're betting again in unified information and data modeling, as I will explain in a few slides. This is the scope. The project is called MetroHaul. You're welcome to visit the MetroHaul webpage, as again, it's a 3-year project funded by the European Commission. There are like 20 partners, including 3 major Telecom Italia, Telefonica, and British Telecom, who is leading the project. We have optical vendors like Korean or ADVA or Ericsson, and research centers and universities. Again, the scope of the project is to address this new kind of metropolitan networks that interface between access and large core with terabits per second, with the idea that we can deploy photonic clouds, so to speak, closer to the user or not so close to the user, depending on the service requirements. So if you look a bit, if you zoom a bit of what's this access metro node, we call it the AMAN node for the lack of a better term. It's a node that interfaces between different access technologies. We can talk about PON, we can talk about mobile backhauling, enterprise access. The idea is that we will be having a common layer 2 aggregation switch layer. We will have, of course, our pool of resources for computing, NFV, and so on. But at the core of the node, there's also this optical technology. And we're focusing this project considering the state of art of optical technology. This means a flexible management of optical spectrum, a sliceable bandwidth variable transceivers, lots of optical details at the state of art that allows us to really have some softwareized programmable optical layer, which is part of the infrastructure. But if you somehow abstract from the details and you try to see this macroscopically, what we're dealing here at the metropolitan level, it's a multi-layer, multi-domain transport network in which we are connecting points of presence, NFBI POPs, and that we have to somehow deal the complexity of automating services across different NFBI POPs in different geographic locations, spanning networks that have huge complexity, at least in the optical layer. So what's the main goal? So in this context, what we want to be able is to deploy VNFs and network services, orchestrate services at large for some definition of service across this metropolitan infrastructure. This means managing the NFVI POPs, managing the aggregation or per site layer 2, layer 3 switching. It could be used in OpenFlow or P4 or any other kind of technology, but also the optical domain that sits there between sites. So what are the choices that we're doing in this project? Our main challenge is how do we address the SDN control of disaggregated optical networks. And you may ask, what's a disaggregated optical network, in case you didn't hear of the term? This is something that's been increasingly talked about in optical conferences such as OFC or ECOC. The idea is that the traditional optical transport networks are used vendor lock-in, are closed systems. At least you have a vendor domain. They can offer open interfaces so you can somehow interact, but the details of what happens in the optical network, it's closed. This limits, as an operator, this limits the ability to do upgrades. You're locked into your vendor. You don't have control. It may happen also that the technology moves at different paces, at different speeds. So maybe the transceiver can do something more, but you're still locked in by the vendor. So this term of disaggregation comes from the computing world and white boxes, where you end up deploying your network by composing and components, transceivers, WSSs, ROADMs, usually those that are more effective or cheaper or more performant. It's up to you. You have a lot of flexibility. We talk about partial or full disaggregation because there are different deployment models. You can go for a partial disaggregation where you still keep your open line system from a given vendor, but you're still able to disaggregate the transceivers, which are commonly the cost factor for an operator of an optical transport network. As you can guess, having this disaggregation of the optical network is giving you the opportunity to talk about a new degree of flexibility. You can migrate components, you can do piecewise upgrades, you can manage the network in a much flexible way. But of course, there are challenges to this. It goes without saying that having a highly integrated system with a vendor behind it, usually it reaches highest performance. So this is still a trade-off to be considered when you talk about disaggregating an optical network. In the context of a metropolitan network, we can still do, because we are not so constrained by the huge performance penalties of huge quality of transmission constraints, so we can still do fine. And from the perspective of the control and management, we need to somehow define the way to control these piecewise or disaggregated optical network. There are initiatives, maybe a couple of pointers. You have the Open ROADM initiative. It's led by Fujitsu, but many other vendors as well, which is a MSA covering pluggable optics, transponders, and ROADMs, so what kind of different models we have. And Open Config is also an operators-led initiative to have vendors that can be used. And within this macro Open Config project, you have some specific models that deal with the optical layer. So if you want to be a bit more visual, what are the challenges that we have to address? We have to address 4 main pillars. First, we need some kind of unified information and data modeling language. We need a language to express data models for devices, for transceivers, for ROADMs, for any kind of WSS, any kind of device that you can deploy in an open line system or in a FlexiGrid optical network. Ideally, it has to be a common language, having huge associated frameworks and tools. Without going into the details, maybe you heard of YANG. YANG is an IETF-defined language that expresses the capabilities of a device in terms of read-write operations, attributes that you can modify, remote procedure calls, notifications. It's like, so to speak, the modern version of SNMP. Along this, let's say, unified information and data modeling language, YANG, you also need an architecture for the remote configuration and control of those devices. There are multiple to choose with. They're all like SDN-like, but the one we're choosing, it's a client server. It's defined by the netconf architecture. In very simple terms, it's a client-server architecture where you have multiple clients, and you can have transactional semantics and so on. So it's called netconf. Again, for those interested, it's an IETF definition of specs. Along with your data modeling language, you need a transport protocol. A transport protocol somehow specifies how do you convey those configuration messages to the device, and we're using also netconf. In short, ideally, like SNMP and MIPS, the data modeling language and the transport protocol should be decoupled. In practice, they are not so decoupled, but still it's a good trade-off. And the fourth main pillar and the challenge that we are addressing as a community is that it's good to have a framework, a protocol, an architecture, everything, but we're lacking, as you may guess, standard models. So the community especially is not able to come up with consensus for what is a model of a device, of a transceiver. Each vendor has its own extension, so this is the hard part. And what we're seeing now is we're having an explosion of modeling of models, some of them overlapping, some of them covering the same functionalities, and this is the complexity that we need to address. How do we how do we cope with this complexity? More from the point of view of architectural. So our point is how do we do, from the SDN point of view, to have an SDN control of a disaggregated optical network. This is a common framework that we're using in the project. In short, what we have here is in blue, is your optical network where you have your devices, ROADMs, reconfigurable add-drop multiplexers, transceivers, transponders. These are mix and match. You can, in theory, deploy your own, or it's a disaggregated network. The common approach is that you end up having an agent on top of each device. That agent implements the netconf protocol. You have a netconf server, and by using these young common models, you can deploy the model in the SDN controller. It can be ONOS or Open Daylight. And it is this huge model-driven development. You feed the young model. There are software tools to automatically compile, generate your APIs, generate your Java classes, your Python classes, everything. So the programmability of the network is automated with this approach. So this is why we call model-driven young netconf control of a disaggregated optical network. Just to show you here how it looks like a young data model and the kind of XML that it's in the netconf edit config messages, but just for information. I'd like to point out that very recently, the ONF, the Open Networking Foundation, has launched the ODTN project. It's Open Disaggregated Transport Networks, and it deals with implementing on top of ONOS this idea of being able to control disaggregated optical transport networks. Telefonica, CTTC, NTT, the ONF are partners of this project. This started a couple of months ago. Okay, that was one part. One part was how do we deal with the optical layer. But as I showed before, the NFBI pods are located in different data centers. They are interconnected by packet switch layers. So from the SDN point of view, we need somehow to deal with a multi-layer, multi-domain network. And in MetroHaul, much like elsewhere, we are covering these by adopting hierarchical SDN models. This means that, in short, you have a network orchestrator or parent controller, call it as you wish, and then you may have one or multiple SDN controllers per domain. The idea is always the same. Your domain is abstracted by your domain controller, and then you have some kind of topology and technology abstraction here, and you end up having some kind of parent controller, parent network orchestrator that somehow works with abstracted topology information, and you're still able to end up setting up end-to-end connections crossing multiple domains. And this is quite a common architecture, and it's being exploited in the IETF. It's called the ACTN architecture, abstraction and control of traffic engineering networks, or including the ONF TAPI, Transport API, framework and models, because at the end, what you end up defining is the protocol between the parent and the controller, so you can have a unified view of your end-to-end network, regardless of who is actually controlling this. So the missing piece is how do we put this in the scope of orchestration, and what's the service platform that we're dealing with in MetroHaul? As you may guess, that's why we're here, we are somehow adopting NFBO, NFB architecture and functional architectures to deploy this service platform. So in short, we end up having a single instance of an NFBO, and then this NFBO may control multiple VIMs, each at one VIM per location or per optical node. And in this specific project, we have selected open source Mano as the NFBO that we're targeting. So we're working in cooperation with Telefonica, University of Bristol, BT, to actually deploy NFBO. And one of the key challenges for our project, I mean, I'm a bit biased, a bit scoped, is that we need somehow to work a lot more in the NFBO WIM interface. How do we plug our hierarchical structure here in such a way that the NFBO can see it as a WIM, and we can end up provisioning network services in this context. So a few more words about this. we have our service platform. It's a research project, so we are allowing ourselves to have a bit more freedom. And what we're trying to do is the optical layer generates a huge amount of telemetry data. So we would like to benefit from this telemetry data, the optical layer, to be able to have even local or network-wise decisions based on this telemetry and data mining. So we're building on systems that rely on this telemetry and monitoring data, and expert guys in the project, not me, are dealing with long-term data analytics and machine learning, artificial intelligence, and how can we improve these using this data. At the physical layer, I can tell you this deals with checking the OSNR, checking the bit error rate, predicting traffic, and those highly mathematical uses of machine learning in network operation. We also want to have the means of extending OSM and the SDN in such a way that our placement algorithms may be holistic and taking into account not only the status of the different VIMs, but taking into account as well the status of the network. And this means also going into the details of the status of the optical network. This is the part that is usually mostly ignored. So I'd like to finish with a couple of slides. Much like in 5G Tango and as a 5G PPP project, we also want to deal with the idea of deploying slices on top of the common infrastructure. So in this case, the common infrastructure ends up being multi-domain, multi-layer metropolitan network, but at the end the concept is the same. If you can virtualize the network, if you can virtualize your resources, you can still allocate virtual infrastructures, and on top of that deploy your slices. And slices can in turn, why not, be controlled by their own SDN control plane or by their own function management. So we will not go much into the detail on that, because as a mainly optical project, we'll be happy if we can just reuse existing components. So our approach will be based on having physical infrastructure providers, which are exported to the upper systems by means of VIMs or WIMs. We can then deploy multiple Mano instances, one per tenant, for example, and each instance will end up deploying one or multiple network services. And answering the question to the previous speaker, we do see quite an analogy one-to-one, at least for the time being. It can be extended on a network service and supporting a network slice. That said, the main challenge is not coming up with this, because I believe that this is quite well understood. It's how do we map these concepts of network slicing to the different technologies that we have at the optical layer. Just to tell you, for example, a transceiver can be a slice, so it supports some kind of multi-user. A ROADM can also support a kind of multi-user approach, or even the spectrum in a fiber can be sliced, and you can split your spectrum, assigning a part of the spectrum to a given tenant or a slice or a virtual network. So this is a bit the end ultimate goal of the project. And to conclude, so if I have to say a bit key messages, again, we're here, so the idea is that we need to automate the provisioning of services. It needs to be done involving heterogeneous resources. In our case, we're focused on the transport network, but also we are adopting this cloud computing and NFV approach. My key message is that, okay, the NFV framework provides a suitable basis, but we need to include the transport network, and we still have some common bases to start from, like hierarchical network control, using open and standard APIs, and we think that Mano and the model-driven SDN are key components of this vision. So that would be all. Thank you very much. If you have any comments.
Thank you, Ramon. A question over here for you?
Yeah.
This looks like great work. I'm thinking about how the disaggregation of your metro optical node fits with the disaggregation of the 5G base station, because we're seeing lots of work in XRAN, ORAN, whatever RAN, okay. And pieces of the base station could well land up inside one of your nodes.
Definitely.
They may also require very fast response to change the state of the optical layer for specific traffic types on the 5G slices in the RAN. Mm-hmm. Is any consideration being made about integration of the management frameworks for disaggregated base stations with disaggregated optical networks?
I fully agree with you. That's the ultimate goal, and I think this is the ultimate goal of the H2025 GPP, including the management of the RAN and the management of the transport network. There are several projects, including MetroHaul, that deal with this, but to my knowledge, none is actually attacking the orchestration planes and the control planes of the mobile network and the transport at the same time. There's been a couple of efforts in that sense, like I think it's the 5G Transformer project or the Cross-Haul project, which are also in the same program. I fully agree with you. In MetroHaul, we are somehow decoupling this. We are considering, on the one hand, the disaggregation of the optical. It means disaggregating the transceiver, disaggregating the ROADM, and so on. But then we know that we are supporting centralized RAN and cloud RAN, where, as you said, we can have a pool of BBUs, the radio head, and the EPC in different locations of the node. This is a main use case for our project. We have also CDN, robotics, but that's the main one. And as you see, the actual traffic variations may imply how do you end up moving your virtual machines. Actual answers to what kind of algorithms or what kind of dynamicity we can support, we don't have them yet. But we have that as a demonstrating use case at the end of the project. Thank you very much.
That's great, Ramon. Very exciting stuff. Thank you very much.
Thank you.